A chemist stood in a courtroom in Kent holding a glass vessel, and inside it was the proof that a young man had murdered his own grandfather. By the time the jury was shown it, the proof had gone. Not destroyed, not stolen, simply degraded into a brownish sludge that looked like nothing at all. The jury acquitted. The young man walked out of the building a free man, and years later, when the law could no longer touch him, he admitted that he had done it. The chemist's name was James Marsh, an ordnance chemist at the Royal Arsenal at Woolwich, and he had done nothing wrong. He had used the standard test of his day correctly on a pot of coffee and on the stomach of a dead farmer, and it had told him the truth. There was arsenic in both. The problem was not the chemistry. The problem was that the answer the chemistry gave him was a yellow precipitate, a fine sediment settling at the bottom of a flask, and a yellow sediment does not keep. The man he had tested for was John Boddle, a farmer's grandson from Plumstead, and the case against him was, in every respect except one, a strong one. He had drawn the water, he had been present when the coffee was made, he stood to inherit. What he did not have to contend with was a piece of physical evidence that a jury could look at and understand, because by the time 12 farmers and shopkeepers filed into the box, the evidence had turned the color of dishwater. So they were asked to convict a man of murder on the word of a chemist describing a color that nobody else could see. They declined to do it, and it is hard to say they were wrong. And if you want the single moment out of which modern forensic science grew, it is probably that one, not a triumph, but a chemist walking home from an assize court having been entirely right and having lost anyway. It is worth being precise about why this mattered so much, because arsenic is not merely one poison among many. For roughly 300 years it was the poison, to the point where in France it had acquired a nickname that tells you everything: powder de succession. Inheritance powder, the substance you used when you had decided not to wait. White arsenic, arsenic trioxide, the form that actually killed people, is a fine white powder with no smell and almost no taste. It dissolves readily in hot liquid. It looks like flour, like sugar, like the powdered chalk that Victorian kitchens were full of, and it could be stirred into gruel or tea or a dose of medicine without anybody noticing anything at all. A fatal dose of white arsenic is somewhere around 100 milligrams, and doses well under that will kill if they are repeated. Enough to kill a grown man would sit on a sixpence and leave room around the edge. That is the first half of the problem. The second half is what it does. Acute arsenic poisoning produces violent vomiting, abdominal cramp, unquenchable thirst and profuse watery diarrhea, followed by collapse, which is to say that it produces almost exactly the clinical picture of cholera, of gastric fever, of the ordinary summer diarrhea that killed people constantly in the 1830s. A doctor called to a house in 1830 to find a man dying in that state had no particular reason to think of murder, and every reason to think of the disease that had killed 4 people down the same street that month. This is the crucial point about arsenic, and it is the reason it lasted so long as a murder weapon. It did not merely go undetected. It arrived pre-explained. There was always an innocent story already sitting on the table when the doctor walked in. And it was everywhere. Arsenic was not a controlled substance, an exotic import, or a thing you needed a contact to obtain. It was sold across the counter of every chemist's shop in Britain, by the pound, to anybody who asked, principally as rat poison and fly powder. It was in sheep dip and weed killer, it was in medicines, it was in wallpaper. If you set out in 1835 to acquire enough arsenic to kill your husband, the difficulty was not obtaining it, it was thinking of a reason to say out loud. So consider what a test for arsenic actually had to do, because the difficulty is not the one most people assume. It is easy enough to detect arsenic in a jar of arsenic. What a criminal investigation needs is something much harder: to find a trace amount of a metal in a few ounces of decomposing human tissue that has been through a stomach, a liver and several weeks in the ground, and then to prove to a room full of non-scientists that the thing you found was really there. The chemists of the early 19th century were not helpless. Johann Metzger had shown in the 1780s that if you heated a substance containing arsenic with charcoal, a thin metallic film would deposit on a cold plate held above it. Valentin Rose had shown, around 1806, that you could get arsenic back out of the contents of a stomach by boiling the tissue away with nitric acid. The knowledge existed, it simply did not yet exist in a form that could survive a courtroom. The standard method by the 1830s was the hydrogen sulfide test. You passed hydrogen sulfide gas through the suspect liquid, and if arsenic was present it threw down a bright yellow precipitate of arsenic trisulfide. As chemistry it worked. As evidence it had 3 defects, and each one of them is instructive. The first is that it was not very sensitive. A small quantity of arsenic in a large quantity of soup produced a faint tinge rather than a bold yellow, and a faint tinge is a matter of opinion. The second is that other things also produce yellow precipitates, so the result was suggestive rather than specific. The third is the one that beat Marsh at Maidstone: the precipitate is unstable. Left in a jar it darkens, clumps and settles, and within days it no longer looks like the thing the chemist saw. Put those together and you have a test that could tell a chemist privately that a man had been poisoned and could tell a jury almost nothing. The evidence existed at the moment of the experiment and then decayed. Everything about the modern idea of physical evidence, that it can be preserved, transporting, produced in court and examined by the other side, was impossible with a result like that. Marsh went back to Woolwich and spent the next few years on the problem, and the solution he arrived at is one of those pieces of apparatus that seems obvious the moment somebody has thought of it. Take the sample, put it in a flask with zinc and dilute sulfuric acid. The acid attacks the zinc and generates hydrogen, and if arsenic is present in any form, the hydrogen combines with it to make a gas called arsine. Arsine is led out of the flask through a drying tube and a fine nozzle. You ignite it, or you heat the tube along its length. And arsine heated falls apart, the hydrogen burns away and the arsenic itself is deposited as a metallic film, a black-brown shining stain, on whatever cold surface you hold in the flame. A plate of porcelain, a piece of glass, the narrow part of the tube. That deposit is the invention. It is metallic arsenic, the element, recovered out of a corpse and put back on a plate where anybody in the room can look at it. It does not fade, it does not settle. It can be sealed in a tube and carried across a country, produced in a court 18 months later and handed along the jury box, and it will look exactly as it looked on the day it was made. Marsh published his method in 1836 in the Edinburgh New Philosophical Journal under a title that is as unglamorous as the man appears to have been, Account of a Method of Separating Small Quantities of Arsenic from Substances with Which It May Be Mixed. The paper is a description of glassware and procedure. It contains no manifesto and makes no claim about justice. It is a recipe. And it was extraordinarily sensitive. In competent hands, the apparatus would show as little as a 50th of a milligram of arsenic, a quantity far below anything the eye could see, far below anything that could hurt anybody, recovered from tissue and displayed as a visible mark. For the first time, a chemist could say to a court not, "I believe there was poison, but here it is, this is some of it, look." That is a change of a kind that does not happen often. Almost every advance in forensic science since has been an improvement in sensitivity or in specificity, finding smaller amounts or telling substances apart more sharply. Marsh's test was an improvement in something else entirely. It made the result durable. It converted a fleeting observation into an object, and an object is a thing the law knows how to handle. Which is also, immediately, a new kind of danger, and to Marsh's credit the profession noticed it quickly. Antimony, a metal used in medicines and in type metal, and in a great many 19th century household preparations, behaves in the apparatus almost exactly as arsenic does. It forms a gas, stibine, and it deposits its own metallic mirror, which to an untrained eye is indistinguishable from the arsenic one. The distinguishing step is small and completely characteristic of how forensic science actually works. An arsenic mirror dissolves in a solution of sodium hypochlorite, ordinary bleach, and an antimony mirror does not. The arsenic mirror is also more volatile and can be driven along the tube by gentle heat. So the test as it settled into practice was not one operation but a sequence: produce the mirror, then prove what the mirror is. Remember that shape because it recurs everywhere in this subject. A technique produces a result. The result is ambiguous in one specific way. A second procedure resolves the ambiguity, and the value of the technique in court depends entirely on whether the analyst bothered with the second procedure, which nobody watching will know either way. It is worth walking through what running the test actually involved, because the distance between a method as published and a method as performed is where forensic evidence usually goes wrong, and that was as true in 1840 as it is now. The analyst starts with tissue, and tissue is the hard part. A liver or a stomach is overwhelmingly organic matter, and organic matter interferes with everything downstream. So the sample has to be destroyed before it can be tested, boiled with nitric acid or with acid and potassium chlorate for hours until the flesh has broken down, and what remains is a clear or straw-colored liquid in which any metal present is in solution. This step is called wet digestion, and it is where arsenic is most easily lost, driven off as vapor by a fire that was allowed to run too hot. Then the apparatus. Zinc in the flask, dilute sulfuric acid added, and a period of waiting before anything is heated, because the flask is full of air and arsine mixed with air will explode. The hydrogen is allowed to sweep the vessel clear first. The gas passes through a tube of calcium chloride to dry it, because water in the tube ruins the deposit, and out through a drawn glass jet. Now the sample goes in, and the analyst heats the tube along its length with a spirit lamp and holds a cold porcelain plate in the jet. If arsenic is present, the mirror begins to form within a minute or two, first as a faint brown bloom, then as a hard black film with a metallic luster where the flame is hottest. Then the confirmations, none of which are optional. Is it soluble in bleach, which would make it arsenic and not antimony? Does it move along the tube under gentle heat, as arsenic does and antimony does not? And crucially, what did the same apparatus produce 5 minutes earlier with no sample in it at all? An analyst who ran the blank, the sample and the confirmations, and wrote all three down, produced evidence that could survive cross-examination for the next 100 years. An analyst who ran only the middle one produced a mirror and an opinion. There was even a rough way of quantifying it, which mattered enormously once ubiquity became the standard defense. Prepare mirrors from known weights of arsenic under identical conditions, keep them sealed as a reference set, and compare the questioned mirror against them by eye. It is crude and it depends entirely on the conditions being genuinely identical, but it converts arsenic is present into arsenic is present in about this much, and that second sentence is the one that answers a wallpaper defense. Which brings the story to Paris and to the man who turned a piece of apparatus into a discipline. The Marsh test on its own is glassware. What was needed alongside it was somebody prepared to answer the harder questions. Where in a body does arsenic go? How long does it stay? How much is normal? And what exactly is a chemist entitled to say in a witness box? Matthew Orfila, the dean of the Paris Faculty of Medicine, is the man usually described as the founder of toxicology, and unusually for such labels it is close to accurate. He was born in Menorca, trained in Valencia and Barcelona, came to Paris as a student and never left. He was a lecturer of formidable popularity, a competent singer, and an obsessive experimentalist in an era when medical men mostly wrote from authority. Orfila had published the founding text of the subject in 1814, while still in his 20s, Traité des poisons terrestres des regnes minéral, végétal et animal au toxicologie générale. A treatise on poisons drawn from the mineral, vegetable and animal kingdoms, or general toxicology. The claim implied by that title is that poisons are a subject in their own right, with their own methods, rather than a corner of medicine or a corner of chemistry. His contribution to the arsenic problem specifically was to insist on two things, both of which sound obvious now and neither of which was standard then. The first was that you must examine the tissues of the body, not only the contents of the stomach. Arsenic is absorbed. It leaves the gut and distributes itself into the liver, the kidneys, the muscles, the bones. A poisoner's best friend was a chemist who tested the stomach, found nothing and stopped. The second was that you must run the test on your own materials first. The zinc and the sulfuric acid used in the apparatus were themselves industrially produced, and industrial zinc of the 1830s routinely contained traces of arsenic. Run the Marsh test with no sample at all, and you could still get a faint mirror. Orfila's rule was that the analyst tests the reagents alone, records what they give, and only then tests the sample. That is the blank. It is the control experiment, in the exact modern sense, arriving in forensic practice in the 1830s, and it is arguably a larger contribution than any individual analysis he ever performed. Every laboratory in the world now runs a blank as a matter of routine. It exists because a Paris professor understood that an instrument sensitive enough to be useful is also sensitive enough to convict on its own contamination. And then, in the winter of 1839, in a decaying building in the Corrèze, a set of circumstances assembled themselves that would put all of this in front of the public at once. The estate was called Le Glandier, and it was not what she had been told. The letters and the marriage broker had described a manor house and an ironworks. What stood there was a converted Carthusian monastery, cold, half-ruined, running with damp, surrounded by an unprofitable forge that was mortgaged past its value. The rats were bad enough that the household bought arsenic for them regularly, which is a detail that mattered enormously later. Marie Lafarge, born Marie Fortunée Capel, was 23 years old and had been raised in Paris on the edge of good society, well enough connected to be invited everywhere, not rich enough to be a real prospect. She had been convent-educated, was widely read, wrote fluently and with self-dramatizing flourish, and was, by every account including hostile ones, extremely intelligent. She had been married off through an agency, essentially as a transaction. Charles Pouch Lafarge, the ironmaster of Le Glandier, was a widower some years older, blunt and provincial, and in serious financial trouble. His interest in the marriage was the dowry. He had misrepresented his estate, and she, or her family, had somewhat misrepresented her fortune, so the arrangement began with both parties having lied to the other about the only thing either of them wanted. What happened next is documented and pitiable. She locked herself in a room on the wedding night and wrote him a letter begging to be released, saying she loved another man and would take poison rather than stay. He refused, a reconciliation of sorts was patched together, and for a few months the marriage functioned. In December 1839, Charles travelled to Paris on business to raise money on a patent for a smelting process, and while he was there, a parcel arrived from home. It contained a cake. The account is that Marie had sent small cakes, and that what arrived was one large one, which is the kind of discrepancy that means nothing at the time and becomes very loud afterwards. He ate some of it that night and was violently ill. He recovered enough to travel, came home in January, and there deteriorated steadily with vomiting and cramps over about a fortnight. He died on the 14th of January 1840. By then the household was already suspicious, and the suspicion had a specific shape. A relative of Charles's had watched Marie stir a white powder into a drink and had, rather than confronting her, kept some of the residue. Marie had signed for arsenic at the local pharmacy, for the rats, she said, and the household did have rats and had bought it before. She had also, it emerged, been asking the household about eggnog and about which foods disguised a bitter taste. And here the case stops being a poisoning and becomes an experiment, because what happened next was the first time a French court, and through the newspapers, the French public watched forensic chemistry argue with itself in the open. The material was tested, it was tested again, and the two results did not agree. The first analysis, performed locally, found arsenic. The chemists of Brive examined the eggnog residue and the stomach contents and reported the presence of arsenic. The defense, quite properly, challenged their competence and their method, and a second examination was ordered, this time using the Marsh apparatus by a different group. That second examination found no arsenic at all. Two teams of chemists had examined the same remains and returned opposite answers, in public, in a capital case, with the whole of France reading the transcripts in the morning papers. It is difficult to overstate how novel this was. The authority of the new science, which had been asserted in journals and lecture theatres, was being tested in the only place that ultimately counts, and its first public performance was a contradiction. The defense, led in part by a young advocate named Charles Lachaud, who would build a considerable career on the case, pressed the advantage and demanded the highest authority available. The court agreed. A message went to Paris, and Orfila came south to Tulle. Exhumed material was re-examined under his direction, and on the 14th of September 1840 he went into the witness box. Orfila told the court three things and no more: that there was arsenic in the body of Charles Lafarge, that it had not come from his reagents, and that it had not come from the earth around the coffin. Each clause of that is a defense argument closed off. Not a speech about the certainty of science, not an opinion about the accused, three factual statements, each of which he had done a specific experiment to support. It is worth sitting with the second and third clauses, because they are the ones that show what had changed. A generation earlier, no chemist would have thought to mention either. Orfila mentioned them because he had anticipated the two ways his result could be wrong: that the apparatus had produced arsenic out of its own materials, and that the body had picked it up from the graveyard soil. He had tested the soil, he had tested the zinc. The jury convicted. Marie Lafarge was sentenced to forced labor for life, which the king commuted to imprisonment. She served 12 years of it before she was released, by then gravely ill with tuberculosis, and she died within months of leaving prison. She had written her memoirs inside. They had sold extremely well, and she maintained her innocence to the end and beyond it. There is a further element in the trial that decided a great deal and had nothing to do with chemistry at all. In the months before her husband's death, Marie Lafarge had been accused of stealing a diamond necklace from a friend at whose house she had stayed, the Vicomtesse de Léatourde. She was prosecuted for it separately and convicted. Her explanation was that the jewels had been given to her to sell discreetly, so that the friend could raise money over an affair she wished to conceal, an account which was elaborate, unverifiable, and entirely characteristic of the letters she wrote all her life. It may even have been true. What is certain is that by the time the poisoning trial began, the jury of Tulle had in front of them a young woman already established as a thief and a fabulist. That is worth naming plainly, because it is the second story running underneath the first one. The Lafarge case is remembered as the trial where forensic chemistry proved itself in public, and it was. It was also a trial in which the accused had already been convicted of something else, in which the local feeling against an outsider from Paris was ferocious, and in which the newspapers had chosen sides before Orfila's train left the station. France divided into Lafargistes and anti-Lafargistes over dinner tables for a decade, which means the honest verdict on the case is more complicated than the one usually given. The chemistry, as far as anybody has ever been able to establish, was sound. Whether the chemistry is what convicted her is a different question, and one that no amount of rereading the transcript can settle. The evidence arrived into a room that had largely made up its mind, which is a thing that has happened to good evidence ever since. There is a coda to the trial that has become the most quoted thing about it. The defense had also written to François Vincent Raspail, a chemist and Republican agitator of great ability and greater self-confidence, who took the brief and set out for Tulle. He arrived after the verdict. His comment on the evidence, endlessly repeated since, was that with the apparatus in question he could find arsenic in the chair of the presiding judge. Which raises the objection that has to be dealt with, because Raspail's remark is not simply a piece of showmanship. It is the single most serious criticism that can be made of a very sensitive test, and it applies to every very sensitive test invented since. If your method can detect a 50th of a milligram, then you will find your substance in places where nobody put it, and the finding will be true and meaningless at the same time. Arsenic genuinely is everywhere. It occurs naturally in soil and in rock, at concentrations that vary from place to place by more than an order of magnitude. It occurs in groundwater. It accumulates in human bone over a lifetime from ordinary diet. It was present in the industrial zinc of the period, in commercial sulfuric acid, in the coal that heated the laboratory, and in the graveyard earth that a coffin sat in for 8 months. So a bare statement that arsenic was found in a body is on its own close to worthless, and by the 1840s the better analysts knew it. The question that carries the weight is not presence but quantity, and the comparison that carries the weight is not with zero, but with what the same test finds in a body nobody claims was poisoned. That comparison is what Orfila's blanks and soil samples were reaching for. This is the same problem the whole field keeps rediscovering. Every technique that becomes sensitive enough to be genuinely useful becomes sensitive enough to find background, and the discipline of a field is measured by how quickly it starts asking what the background is. Toxicology got there fast, because Raspel said the thing out loud in front of the entire French press, and the profession could not pretend it had not been said. And the background in the 19th century was substantial, because arsenic had industrial and domestic uses that put it into ordinary rooms in quantity. Carl Wilhelm Scheele had produced a brilliant green pigment from copper and arsenic in 1775, and by the 1830s Scheele's green and its successor emerald green were in wallpaper, in paint, in fabric dye, in artificial flowers, and in the coloring of confectionery. The wallpaper case is the memorable one. Damp walls papered in arsenical green grew mold, and in 1893 an Italian physician, Bartolomeo Gosio, showed that certain molds acting on arsenical pigment release an arsenic-bearing vapor. Long before that was understood, doctors had noticed families becoming chronically ill in green rooms and well again when they left them, and had been unable to say why. Medicine contributed as well. Fowler's solution was 1% potassium arsenite in water, flavored with lavender, and it was prescribed through the whole of the 19th century for asthma, for skin disease, for fevers, for malaria, and for more or less anything else that a physician wanted to be seen doing something about. Perfectly respectable patients took arsenic by the spoonful for years. Which means that a Victorian corpse could contain arsenic for reasons that had nothing whatever to do with murder, from medicine, from a bedroom wall, from an occupation, from a green dress. Any competent defense in an arsenic case after about 1850 was going to raise every one of those, and the prosecution's answer had to be about amount and distribution rather than about mere presence. The most sobering demonstration of how much arsenic was simply lying around had nothing to do with any murder at all. In Bradford in 1858, a sweetmaker's supplier sent, instead of the powdered gypsum routinely used to bulk out cheap confectionery, a cask of arsenic trioxide. It was mixed into peppermint humbugs, and the humbugs were sold from a market stall on a Saturday night. More than 200 people were poisoned in a single evening, and 21 of them died, and most of those were children. That is more than the Lafarge case, the Smith case and the Maybrick case put together, every celebrated arsenic murder of the century, outdone in one night by a man reaching into the wrong barrel in a warehouse in Yorkshire. Nobody was convicted of anything much. The horror of it was precisely that no crime in the ordinary sense had occurred. An unlabeled cask, a druggist's assistant, a sweetmaker who noticed the mixture looked wrong and used it anyway. It is the clearest possible statement of the actual situation, which is that a substance capable of killing a street full of people was moving through commerce with less control than flour. The law arrived late, as it usually does, and it arrived because of accidents and scandals rather than because of any single case. Through the 1840s, the newspapers ran a steady traffic in arsenic murders, real and imagined, and by mid-century there was a settled public belief, probably exaggerated, certainly useful to editors, that quiet domestic poisoning was epidemic among the working poor. Parliament passed an act to regulate the sale of arsenic in 1851, and its provisions are worth stating precisely, because they are the ancestor of every controlled substance register since. Every sale was to be entered in a book kept for the purpose, with the date, the purchaser's name and address, the quantity and the stated purpose, and the purchaser was to sign it. Sales to anyone under 21 were prohibited, and the buyer had to be known to the seller or vouched for by a witness. And then the provision that shows somebody had thought about the actual problem. Any quantity under £10 had to be coloured before it left the shop, mixed with soot or with indigo, 1 part in 100, so that white arsenic could no longer be white. You cannot stir a blue-black powder into a bowl of gruel unnoticed. The act did not try to stop people obtaining arsenic. It tried to stop arsenic looking like food. That is a genuinely clever piece of legislation, and it is a useful corrective to the assumption that the law only ever bans things. The coloring rule attacked the specific property that made the substance dangerous in the specific way it was dangerous, and left every legitimate use, the rat poison, the sheep dip, the weed killer, completely intact. There was also a provision that did not survive, and it is revealing about the period. During the bill's passage, it was proposed that arsenic should not be sold to women at all, on the reasoning that domestic poisoning was a female crime. The clause was argued over and dropped, partly on the practical ground that the women of a household were the people who bought the rat poison. The proposal tells you what the legislators believed. Its removal tells you that somebody in the room was thinking. The Pharmacy Act of 1868 extended the same logic much further, defining schedules of poisons, restricting their sale to registered pharmaceutical chemists, and requiring labeling and record-keeping across the whole class. The framework that governs a modern pharmacy counter is, in its bones, the Bradford Humbugs and the Poison Book. Meanwhile, the test was doing its work, and the second half of the 19th century produced the celebrated cases that shaped how the public understood poisoning for 100 years. They are worth going through, not for the gore, but because each one exposes a different limitation in what a chemical test can actually settle. Mary Ann Cotton, a nurse and housekeeper from West Auckland in County Durham, was hanged at Durham Jail on the 24th of March 1873. She was convicted of poisoning her stepson Charles Edward with arsenic after a parish official refused to admit the boy to the workhouse, and she remarked that he would not trouble her long. He died within days. The doctor kept samples and the samples were tested. She was convicted of 1 death and suspected in as many as 21. 3 husbands, a lover, a friend, and a long succession of her own and other people's children had died around her over roughly 2 decades, most of them certified as gastric fever, several of them insured. Nobody had connected them because she moved from Durham to Sunderland to Northumberland and back, and each death was registered by a different doctor who had no way of knowing about the last one. That is the point of Cotton for our purposes. The chemistry that convicted her was not difficult. By 1873, the Range test and the Marsh test were routine, and a competent county analyst could run either. What had protected her for 20 years was not the undetectability of arsenic. It was the absence of any system that could notice a pattern across parishes. A test only works on a sample somebody thought to take. There is a second thing about Cotton that explains a great deal about Victorian poisoning generally, which is the money. Several of the deaths around her were insured. Working-class families of the period paid into burial clubs, friendly societies that took a subscription of a penny or 2 a week and paid out a few pounds on a death, so that a household could bury a relative without the disgrace of a pauper funeral. The purpose was decent and the need was real, the arithmetic was not. A few pounds was a serious sum to a family living on perhaps £1 a week, and nothing prevented a child being enrolled in more than 1 club at once. Parliament worried about this openly in the 1840s, and the sanitary reformers who investigated burial practice said in print what everybody suspected, that a system paying out on the death of a child, in a decade when a great many children died anyway, had built an incentive into itself and then walked away. That is the context that turned arsenic into what the Victorians understood as a poor person's crime, and it is why the debates about the 1851 Act keep sliding into remarks about servants and about women. The pattern was real enough, the money was small, the deaths were unremarkable, and the poison cost a few pence, but the conclusions drawn from it were about class as much as about evidence, and the legislation carries the fingerprints of both. Madeline Smith, tried in Glasgow in 1857, illustrates the opposite failure. Her lover, Pierre-Émile Elangelier, died of a massive dose of arsenic. She had bought arsenic 3 times, signing the poison book, saying it was for her complexion, a fashionable and not implausible claim at the time. She had written him letters of extraordinary intimacy and had lately been trying to retrieve them because she was engaged to somebody else. The chemistry was solid. The arsenic in Elangelier was found, measured, and beyond argument. What could not be established was contact. There was no proof that the two had met on the relevant night, and there was evidence that Elangelier had himself talked about taking arsenic. The Scottish jury returned a verdict of not proven, and she lived another 50 years. Motive and means were both present. The test could say nothing about the third thing. Florence Maybrick, tried in Liverpool in 1889, is the case that shows a defense turning the ubiquity problem into a weapon. Her husband James, a cotton broker, died after an illness, and arsenic was found in his body. She had been soaking flypapers in water, flypapers being arsenical, which she said was to make a cosmetic wash. She had also, indisputably, been having an affair. The difficulty was that James Maybrick was a habitual taker of arsenic and other drugs, apparently for years, and had been buying tonics containing it. So the arsenic in his body had at least two plausible sources, and the amount recovered was not obviously fatal. The trial was presided over by a judge whose summing up is generally regarded as a disgrace, and she was convicted, reprieved from hanging and released after 15 years, a verdict very few people have ever defended. The Maybrick defense rested partly on a genuine phenomenon that has fascinated toxicologists ever since. In Styria in the Austrian Alps, there were peasants who reportedly ate arsenic deliberately, in small, gradually increasing doses, for stamina at altitude and for a bright complexion, and who tolerated quantities that would kill an ordinary person. The accounts are disputed in detail, but the physiological principle of acquired tolerance is real. So even after the test is perfect, the interpretation is not. A precise measurement of arsenic in a liver answers one question exactly and leaves three others wide open: how it got there, over what period, and whether it was the cause of death. That is the permanent structure of forensic evidence, and it is why the best analysts of every era have been noticeably more cautious in court than the newspapers reporting them. What the test did do, unambiguously, is end arsenic as a rational choice for a murderer. This is the part that gets least attention and matters most. Detection does not merely catch offenders, it changes what offenders do. A method that leaves permanent, demonstrable, court-ready proof in the victim's own tissue is not a method a thinking person selects, and the rate of arsenic poisoning fell through the later 19th century and collapsed in the 20th. Which leaves the question of what happened to the man who started it. Marsh died in 1846 at 52, having received the gold medal of the Society of Arts for the test and remarkably little else. He remained an ordnance chemist on a modest salary, took out no patent worth speaking of, and left his family in circumstances poor enough that the accounts of his death are uniformly embarrassed about it. There is no moral in that beyond the obvious one, but it is worth recording because the shape recurs. The pollen case in Austria, the wood grain analysis of a ladder, the identification of insects on a body, the founding work in forensic science is done again and again by people who were not building forensic science and who mostly did not profit from having built it. Marsh was solving a problem that had annoyed him professionally. The technique itself had a long life. The Marsh test remained in use in more or less Marsh's form for well over a century. The range test, dipping a strip of copper foil into acidified sample, where arsenic deposits as a dull grey film, arrived in 1841 and was simpler and quicker, though less sensitive, and the two were often run together. Both are still occasionally taught, because watching a mirror form is a better lesson in what an analytical result is than any amount of instrument output. What replaced them is a different order of thing entirely. Atomic absorption spectroscopy, developed in the 1950s, measures how strongly a vaporized sample absorbs light at a wavelength characteristic of a particular element and gives a number rather than a stain. Inductively coupled plasma mass spectrometry, now standard, ionizes the sample in an argon plasma and counts atoms by mass, quantifying arsenic in the parts per billion range in minutes. That capability opens a question Marsh could never have asked, which is not whether arsenic is present, but when it arrived. Hair grows at roughly a centimeter a month, and it incorporates arsenic from the blood as it grows, so a single hair is a rough chronological record. Cut it into segments, analyze each segment, and the resulting profile distinguishes a single large dose from repeated small ones and dates them. That technique is why the argument about Napoleon's death has run for 60 years without resolving. High arsenic levels have been measured in hair attributed to him repeatedly by good laboratories, and the finding is real. What it means is not, because arsenic was in the hair preparations, the wallpaper, the medicines, and the wine of his time, and because the provenance of 200-year-old hair is exactly the sort of thing that cannot be nailed down. A perfect measurement of an uncertain sample is still uncertain, which is the argument for spending 40 minutes on a piece of 1830s glassware. The apparatus is obsolete. Everything it was built to establish is now done faster, better, and to a smaller decimal by a machine that runs unattended overnight. What is not obsolete is the set of habits that grew up around it, and those habits were not obvious, and they were all bought at the price of a case that went wrong. The first is that evidence must persist. Marsh's real insight at Maidstone was not chemical at all. It was that a result nobody else can inspect is not evidence, whatever it proves to the person who saw it. Every modern requirement about retained samples, sealed exhibits, documented chains of custody and independent retesting descends from a jury looking at a jar of brown sludge and quite reasonably declining to hang a man on it. The second is the blank. Orfila's insistence on testing the reagents before the sample is the whole of quality control in embryo, the recognition that a sufficiently good instrument will find your substance in your own equipment, and that a result which has not been controlled against that possibility is not a result. Every laboratory on Earth now runs blanks, and the reason is a Paris professor who understood what Raspel's joke about the judge's chair actually meant. The third is the discipline of saying only what the experiment supports. Orfila's 3 sentences at Tulle are read as a piece of expert testimony close to a model. He said what he found, and he said which 2 alternative explanations he had specifically tested and excluded. He did not say she was guilty. He was not asked to, and if he had been asked, he would have been the wrong person to answer. And the fourth is the one that is hardest to build and easiest to lose, which is that a test only exists where somebody thinks to apply it. Mary Ann Cotton was not protected by chemistry. She was protected by the fact that 20 deaths in 4 parishes were 20 separate pieces of paper. The chemistry that convicted her had been available for a generation. What had been missing was the far duller apparatus of somebody noticing. That is the thought worth taking away from all of it. The age of arsenic ended not when the poison became weaker, but when it became visible. And it became visible because a man who had lost a case in front of a jury spent 4 years making sure that the next chemist in his position would have something to put in their hand. He was not trying to end an era, he was trying not to be humiliated twice. There is one last detail that belongs at the end rather than the beginning. John Boddle, acquitted at Maidstone because a yellow sediment had turned brown, is said to have confessed to the murder afterwards, in the safety of a verdict that could not be revisited. If the account is right, then the whole of this, the apparatus, the discipline, the poison book, the collapse of an entire method of murder, began with a man walking out of a courtroom knowing he had got away with it, and a chemist watching him go. And the substance that had been called inheritance powder for 3 centuries, the one that arrived pre-explained that looked like flour, that killed like cholera, became, over about 30 years, the single worst choice a poisoner could make. Not because anybody outlawed it, because a stain that would not fade turned out to be worth more than any amount of certainty that faded.